Okay, so I'm live streaming it now on YouTube. And then what I'm going to do is save it and post the link in the module section. All right, so let me get out of, whoops. Give me 1 minute here. All right, so let me, oh Lord, what's this? Okay, all right, so I just went live on YouTube, so I'm going to save it and post the link in Canvas in the, under the modules link, so look out for that. All right, okay, so that's it as far as the solubility of oxygen in or any other gas in water, all right? Okay, so let me see if I can cover this topic in the next 10 minutes and then we'll take another break. So now that we have looked at the relationship between the solubility of a gas in water and temperature, we're going to look at also the solubility of a gas and the pressure of that gas above the water. And there's an equation or a law which basically talks about that. It's known as Henry's law. And Henry's law says, as you can see here, that the solubility of a gas in a liquid is proportional to the pressure of the gas over the solution, right? So that's basically Henry's law. So what does that mean? That means that, well, mathematically speaking, we can express it like this. Concentration of a gas is equal to the a constant K times the pressure of the gas over the solution, right? So these are the terms in this equation. C is the concentration, usually expressed in molarity, but not necessarily. P is the pressure of the gas, and P can be expressed in any of the normal pressure units, atmospheres, millimeters, mercury, etc. And K is a constant, right? And the constant K here is dependent only on the temperature, all right? So what we're saying here is that if you have a gas trapped above a liquid in a container, right? What you'll find is that if the pressure of the gas is low above the liquid, then the concentration of the gas, the concentration of the gas would be low in the solution. Correspondingly, if the pressure of the gas is high above the solution, then the concentration of the gas in the solution is also high, right? So there's a direct linear relationship between the concentration of a gas and the pressure of the gas above the solution, all right? So that's basically what Henry's law is all about. So with that said, let me go back to the assignment, because now we should be able to answer this question. So this question is based on Henry's law. So let me just read the question carefully so that we're all on the same page. It says the concentration of hydrogen sulfide in hot springs is relatively high. This accounts for the rotten egg smell around the mud pots in Yellowstone National Park. The solubility of H2S in water is 0.0923 m at 1.00 atmospheres. If the partial pressure of hydrogen sulfide at Yellowstone is 0.012 atmospheres, calculate the molarity of H2S in the mud pots. Okay, so remember the equation I just introduced to you. Let me write it here as soon as I can get this thing. Okay, so let me just squeeze that equation over here. And that is C, the concentration, is equal to K times P. Okay, I'm hearing some noise in the background. So if you could all mute your mics, please. Okay, so this is the equation that you'll be working with. So the question says it gives you the initial pressure, the initial concentration, right? And pressure, right? So basically we can find out what K is. So K is equal to C divided by P, which is equal to 0.0923 m divided by 1.00 atmospheres. And that would mean that K is equal to 0.0923 m over atmospheres. Then the question says that the pressure of the hydrogen sulfide at Yellowstone, is 0.12 atmospheres. And the question is asking for the molarity, right? So in other words, in this case, the question is asking for the concentration. So basically they gave you the pressure, and K, we know what it is. K is this. We just calculated it. So therefore C, the concentration or the molarity, would be equal to K, which is 0.0923 M over atmospheres, multiplied by the pressure, which is given as 0.12 atmospheres. And when I did that calculation, the answer I got is 1.1 times 10 to the minus 2 M. And that's basically how that is done. All right. Okay, any questions about this example? Any questions? Okay. Let me see here. Hold on 1 minute. All right. So let's scroll down to. Can I clear this? Anybody? Can I clear this? Okay. So let me do so. Okay, so let me scroll down to question number 4. All right, so let's look at question number 4. Again, this is based on Henry's law. Let me just write down Henry's law to the side so that you can have it to refer to. Henry's law is C is equal to KP, right? So this is what we'll be using. Remember, C is the concentration, and P is the pressure, and K is just basically a constant. All right. Okay. So number 4 says a carbonated beverage is made by saturating water with carbon dioxide at 0 degrees Celsius and a pressure of 3.0 atmospheres. The bottle is then opened at room temperature, 25 degrees Celsius, and comes to equilibrium with air in the room containing carbon dioxide, where the pressure is 3.4 times 10 to the minus 4 atmospheres. And the Henry's law constant for the solubility of CO2 in water is 0.0769 M over ATM at 0 degrees Celsius and 0.0313 M over ATM at 25 degrees Celsius. So the first question is, what is the concentration of carbon dioxide in the bottle before it is opened? Okay, so the question is a bit wordy, but you need to be able to, when it comes to questions like these, you need to be able to pick out the important information, especially the numbers and what they represent. Okay, so any ideas as to how you would tackle the A part? The question is, what is the concentration of carbon dioxide in the bottle before it is open?
So if we have, so we have K and P.
Okay. Well, we don't have, oh yes, we have K. I'm sorry, you're right. You're absolutely right. You have K and you have P. So what?
So, so P would be 3.4 times
Okay.
10.
Okay, so, well, wait a minute, you sure? Because there are 2 pressures given.
Okay,
You're given this one, and you're given this one. This is the
okay,
one
so
that
then it would
is,
be 3.
exactly, because that's the one where the pressure is before you open up the bottle, right? So
Yes.
the concentration in this case would be equal to K. So what is the K value?
0.0769.
Exactly, 0.0769 M over ATM multiplied by, as you said before, 3.0 ATM. Very good. So when I did that calculation, I got, let me see here. I got 0.23. So let me write this down. 0.23 M, right? So that would be the molarity of the carbon dioxide before we open up the bottle. All right. All right. Tell you what. Going to take another break, another 10-minute break, and then we're going to continue looking at the rest of the questions. All right. We're going to look at the B part, and that's it. All right. And then we'll continue. All right. So I'll be back by 12:10. All right. Ah. I think this is the closest I've ever. Okay, folks, I am back. All right, so let's continue with the second part of that question. And I see somebody has a question. When I go to assignment 1 in Canvas, it doesn't have anything there. Oh, okay, thank you for letting me know. Let me see if I can publish it right now. Okay, assignments. Oh, it should be there. Let me see here. Hold on. Okay, so the person who asked the question is Alexandra. You said that when I go to assignment 1 in Canvas, it doesn't have anything there. I don't know why not, because it should be. Let me just do one more check here. Yes, you should be able to access it. I don't know if you went to the right place. Oh, I know what happened. Okay, my bad. I think I understand what's happening. What you should have done is go to Files. Right? So let me just show you here on the screen. You go to Files. And okay, so this is Files here. And then you go to Assignments. And that's where assignment 1 is located. Sorry about that. Okay, did you locate it, Miss McCoy? No, because you won't be finished with it today. When you're finished with it, then I'll create a Dropbox for it so that you'll be able to upload the completed assignment, right? So don't worry about uploading it now. Worry about completing it, which is what we're doing. All right? Okay, so where were we? We were doing let me go. We were doing the second part of question number the B part for question number 2. I mean number 4. Oh, let me see. Okay. So let me make this larger. And oh, actually, yeah, okay. So for question number 4, B, it says, what is the concentration of carbon dioxide in the bottle after it has been opened and come to equilibrium with the air? So, any ideas as to how we can tackle this problem?
You basically just do the same thing as part A, but with the second set of numbers.
Okay, okay, so I need you to tell me what to write down. So,
may I see the question, please?
okay, what question? You mean the earlier part?
Yes.
Okay, so the earlier part is this right here?
Yes.
Okay.
So K, would K be 0.01 or 0.0313?
Yep. Mhm.
And then the pressure would be 3.4 times 10 to the negative 4.
Exactly. So that means that down here, whoops, scroll too far. So that means that down here, to get the concentration that would be equal to the K, which is, as you said, 0.0313 M over ATM, multiplied by the pressure, which is 3.4 times 10 to the minus 4 atmospheres. And the atmosphere units will cancel out. And according to my calculations, this works out to be equal to 1.1 times 10 to the minus 5 M. And that's basically how that is done. All right. Okay, any questions concerning this one? Any questions? Okay, can I clear this? Okay, let me clear this now. And let me do that. Let me see if there's any other questions. Okay, so going back to the PowerPoint. By the way, what time does this class end? I'm losing track. Oh, 1:10, okay. Just making sure. All right, so let's go back to the PowerPoint. Now we're going to get into what we call the colligative properties of solutions, right? So let's understand what we mean by that term. Let me just check the chat here. Okay, thank you, Ms. Monahar. So basically, when we're talking about the colligative properties of a solution, we're talking about those properties that depend only on the number of solute particles present in a solution and not on the nature of those particles, right? So these are properties which are not affected by the actual nature of the particles, but only on the number of particles, all right, of solute in the solution. So we're going to learn about 4 colligative properties. One is the vapor pressure lowering. The other one is the boiling point elevation. The next one is a freezing point depression. And then the last one is osmotic pressure, all right? So let's talk about vapor pressure lowering, right? So basically, the equation you're looking at here is known as Raoult's law, right? And this law relates the vapor pressure of a solvent to the vapor pressure of a solution, depending on the mole fraction of the solute or the solvent that is present in the solution, all right? So that's the relationship here. So P10, that represents the vapor pressure of the pure solvent, X1 represents the mole fraction of that solvent, and P1, and I'm just realizing that that is not indicated here, so let me make a note of it here. P1 is equal to the vapor pressure of the solvent in solution, all right? So this is after you add a solute to it. Okay, so here it says, if the solution contains only one solute, then we can write down this relationship between the mole fraction of solute 1 and the mole fraction of solute 2. If there's only one solute, that means that the sum of the mole fraction will be equal to 1, which means that the mole fraction of solute 1 would be 1 minus the mole fraction of solute 2. So therefore, we can calculate the lowering of the vapor pressure, which would be the difference between the vapor pressure of the pure solvent and the vapor pressure of the solvent in the solution, all right? That would be equal to delta P. And it turns out that that would be equal to the mole fraction of solute 2 times the vapor pressure of the pure solvent, all right? Now, let me just see if I can show you how we derive this equation. So what I'm going to do here, let me go to my writing function here again. Okay, so basically, this here which is equal to the mole fraction of the solvent, will go here in this equation, all right? So therefore, X1 will be equal to, no, I'm sorry. P1 will be equal to 1 minus X2 times P10, right? And therefore, delta P, hope I have enough space here, will be equal to P10 minus 1 minus X2 times P10, which is equal to P10 minus 1. Okay, this is getting out of hand. I'm sorry, minus P10 minus X2 P0. So P10 minus P10 will give you 0. So therefore, and this will be plus. So therefore, delta P will be equal to X2 P0, P10, which is what we have here. All right. So what I was just showing you is how this equation here is derived. All right. Okay. So enough of that. Let me clear this. Oops. Oh, I guess all right. Let me get on this here. All right, so let's talk about a situation where we have two liquids, right? And let's say that the two liquids are very similar in terms of their polar nature, in terms of the molecules. Now, the example that we're looking at here is a mixture of benzene and toluene. Two very similar, they're different compounds, but they're similar in terms of the molecular interactions, all right? Because they're both nonpolar. So what you're looking at here is a plot of the vapor pressure on the y-axis versus the mole fraction of benzene on the x-axis, all right? And then we have this dotted line here, which represents the variation in the vapor pressure of benzene as the mole fraction of benzene increases from 0 to 1. And then this line here represents the variation in toluene as the mole fraction decreases going from here to here. All right? Because you need to remember that as the mole fraction of one component increases, the mole fraction of the other component decreases in the mixture, right? And that's how we get this line for the toluene. Now, this solid line here represents the sum total vapor pressures of both toluene and benzene under different mole fraction values, right? So as you can see here, the total pressure is equal to the vapor pressure of benzene plus the vapor pressure of toluene, which is basically Dalton's law, which you learned about in General Chemistry 1, right? So basically, for example, if I were to look at where the mole fraction of benzene is 0.2, so let me just make a mark right here, 0.2, right? Which means that the mole fraction of toluene is equal to 0.8, all right? So basically, if I were to draw a line here, right, and then draw a horizontal line here, that would represent the vapor pressure of benzene, right? And then if I were to continue that line here to intersect with that line and then draw a horizontal here, that would be the vapor pressure of toluene, all right? And if I were to continue to draw the horizontal line until it touches the solid line, okay, until it touches the solid line, then that would represent the total pressure, the total vapor pressure above the solution, right? And the total vapor pressure here, which is just short of 400, will be equal to the vapor pressure represented by this part right here, whatever that is, and the vapor pressure here. So this vapor pressure for benzene plus this vapor pressure for toluene will be equal to the total vapor pressure as indicated in this equation right here. All right. So that's basically how we interpret this particular graph. All right. Now, there's one assumption that is being made in this graph, and that is, whoops, hold on. Okay, and that is that the intermolecular forces between the molecules in benzene would be similar to the intermolecular forces between the molecules in toluene, such that when they're mixed together, there's no change in the vapor pressure of the individual components in the mixture, and therefore the total vapor pressure would simply be the sum of those two. In that particular situation, we're talking about what is known as an ideal solution, right? An ideal solution is basically one where the intermolecular forces that exist between the molecules in the separate components would be the same when they're mixed together, all right? And basically what you're looking at here on this side are the equations that are involved. So in the case of two mixtures or two components in a mixture, one component is A, the other one is B. This is the equation for the vapor pressure of component A. This is the equation for the B component, all right, in the mixture. And therefore the total pressure would be equal to PA plus PB, which means that you add this term to get this equation, all right? Now, if one of them is non-volatile, let me make a note of this here. So let's say, for example, if B is non-volatile, what that means is that it does not produce a vapor, like a solid, right? If B is a solid and it's non-volatile, that means that PB0 is 0, right? So if the vapor pressure of B is 0, that means that the total vapor pressure of the solution would simply be equal to the mole fraction of A times the vapor pressure of pure A, all right? And there are some situations where that would be the case. For example, if I were to add, let's say, sucrose to water, well, sucrose being a solid will not exhibit or exert any vapor pressure. So therefore, we don't take that into account when it comes to calculating the vapor pressure of the solution. The vapor pressure of the solution resulting would simply be the mole fraction of the solvent times the vapor pressure of the pure solvent, all right? And I think the next question in the assignment deals with that particular situation, all right? Okay, before I leave this page, any questions about what I just covered? Any questions? Any questions? I want to make sure that you understood what we were discussing on this page. Any questions? Okay. So, what I talked about in the previous slide was dealing with an ideal solution. Of course, not all solutions are ideal. We can have solutions that are non-ideal in a positive and negative way. So what do we mean by that? Well, there are some solutions where the vapor pressure above the solution is actually greater than the total vapor pressure of the components in the mixture, right? And that is demonstrated by the graph here on the left, all right? So this line here represents the vapor pressure of the A component. This line here represents the vapor pressure of the B component. And this line here represents the total pressure. As you can see, it does not fall on the straight line that you see here. So therefore, this here is what we call a positive deviation. Let me write that down here. So we say that this solution exhibits a positive deviation from Rayleigh law. Law. All right. And then the opposite is happening over on this side, where the total pressure will be lower. Whoops, I'm sorry. The total pressure here would be lower compared to what is expected if the solution was ideal. So we say that in this case, the solution is exhibiting a negative deviation. So negative deviation from Raoult's law. All right. And the reason why we have these deviations is because there's a difference in forces that exist in the separate components compared to the forces that exist between the molecules in the mixture. So for example, over here, let me go back to my pointer here. Over here, as you can see here, the force of attraction that exists between the AA and BB molecules, right? Or the A to A attraction and B to B attraction. Those forces here would be greater compared to the force of attraction that exists between the different components, the A and B components. And therefore, what happens is that the vapor pressure would be greater compared to what is expected for ideal solution. And then the opposite is true on the other side here, where the force of attraction that exists between the individual molecules separately would be less compared to the force of attraction in the resulting solution. And therefore, as a result, the vapor pressure of that solution would be less compared to what you'd expect for an ideal solution. All right, so that's where we have the positive and negative deviation from the ideal solution situation. Okay, so any questions about this? Any questions about what I just covered here with respect to positive and negative deviations from Raoult's law? Okay, so the next, okay, so I'm just going to talk about this briefly. This you're looking at on the screen here is basically a diagram showing you the setup for fractional distillation. Distillation, generally speaking, is basically a way of separating two liquids by exploiting their differences in their boiling points. And the basic premise of distillation is that you heat the liquid mixture, and if the boiling points are significantly different, then the lower boiling point liquid will boil first, convert to a vapor, and then you find some means of collecting that vapor, condensing it, and basically directing it into the appropriate receptacle, right? Leaving behind the higher boiling point liquid. So that is what is being demonstrated here. And you have different types of distillation. You have simple distillation, fractional distillation, which is what is being shown here. And there, you have some other, distillation types. And the type of distillation that you would use is pretty much dependent on the kind of solution. Simple distillation is used usually when the boiling point difference is at least 30 degrees Celsius, all right? So, simple distillation is very effective for that usage. And simple distillation looks similar to what you're seeing here on the screen, with the only difference that you don't have this condenser right here, which is known as a fractionating column, right? So if you can imagine this distilling flask being attached directly to right here, then you'll have the setup for the simple distillation. However, this is showing you the fractional distillation. And what makes this better is that you can use this to separate mixtures where the boiling points are closer. And the way this works is when you heat your mixture right here, the vapor that emerges will have a mixture of the two components. Let's assume that we have two components here. The vapor above will have a mixture of two components, right? As it moves up here, what happens is that it condenses, right? And when it condenses, basically what's going to happen is that more vapor will be moving up because the heating here will be continuous, and it will heat the vapor that is moving up will heat the mixture that is condensing here. Now the vapors resulting from that heating will have more of the lower boiling point component in the mixture. And that process of cooling and reheating and vaporizing will continue all the way up to the column until when it emerges from here, you will have the pure lower boiling point liquid emerging from here, and that will be moving down here into the condenser, which condenses the vapor to the liquid, and therefore you're going to get droplets rolling down here and collecting in the receiving flask right here. So that's basically how the fractional distillation apparatus works. Okay, so much for that. So let's talk about boiling point elevation, which is the second type of colligative property that we'll be looking at in this chapter. All right, so let me explain what's happening here in this graph. So what this graph is showing is a plot of pressure versus temperature on the x-axis. Now, let me explain what these lines here mean. Now, I want us for the time being to focus on the solid lines. This line here, and this line here. Okay, so let me explain what these lines represent. These lines represent different temperatures and pressure where you have equilibrium between different states, right? So for example, this line here represents the different vapors and temperatures where we have the equilibrium between the solid state and the vapor state. This line here represents the different temperatures and pressures where we have the equilibrium between the solid state and the liquid state. This line here represents the different temperatures and pressures where we have the equilibrium between the liquid state and the vapor state, all right? So that's basically what these solid lines represent. And it's based on these lines we can determine things like the boiling point or melting point of a particular substance based on the current external pressure, all right? Now, what we're going to look at is how a solution or how adding a solute to a solvent lowers the boiling point of the solution compared to the pure solvent. So we'll be focusing on this part right here, all right? So basically, the boiling point, and I think this is right, that's indeed the case. This is for water, right? So this graph basically represents the situation for pure water, right? This particular line right here represents, as I said before, the various pressures and temperatures where the liquid and vapor exist in equilibrium. All right, now, let's remind ourselves of what we mean by the term boiling point. Now, to the non-chemist or the non-scientist, one may be tempted to say that the boiling point of a liquid is the temperature at which it boils, right? But that's not the case. That's not the actual definition. So let me make sure, write down the definition here. The boiling point is the temperature when the vapor pressure of the liquid is equal to the external pressure. All right? That's the definition of the boiling point. So basically, if we're talking about the current atmospheric pressure being 1 atmosphere, that means that if the pressure is 1 atmosphere, then to get the boiling point of water, all we have to do is draw a line across like this. And then when it hits a solid line, we drop a vertical down here. And this temperature here, where it cuts the x-axis, would be the boiling point of water, which is 100 degrees Celsius. So that's the temperature at which water boils, right? Now, let's look at what happens when we add a solute to the solvent. When we add a solute to the solvent, if you remember what we discussed the last time, what happens is that the vapor pressure of the solution will be less than that of the pure water. And that difference is represented by the dotted line right here. This is a dotted line for the solution, right? That is created when you add a solute to it, right? So basically, if you think about the boiling point of water being here, let me go back to my pen function. If you think about the boiling point of water being here, right? Which means that the vapor pressure is at 1 atmosphere. When you add your solute to the water at that temperature, what will happen is that the vapor pressure will decrease. So the new vapor pressure would be about here, right? So that means that that would not be the boiling point of water because the current or the external pressure is 1 atmosphere. So how do we get to the boiling point of the solution? what we'd have to do is increase the temperature so that the vapor pressure becomes equal to the 1 atmosphere, right? Which means that the new boiling point would be obtained by dropping the vertical down here to get the boiling point of the solution, which obviously is going to be higher than the boiling point of the pure water. So what we're saying is that the boiling point of the solution will be elevated compared to the boiling point of pure water. So basically, some equations here to show you what's happening. In fact, let me erase. Let me erase what I had up here. Okay, so basically, there will be an elevation in the boiling point when the solution is created. And that elevation of boiling point is given by this equation here. Okay, where is it? Hold on. Okay, so that elevation in boiling point is given by this equation. Delta TB, that's the elevation in boiling point, would be equal to the boiling point of the solution minus the boiling point of the pure solvent, all right? So that's delta TB, right? So TB0 would be the boiling point of the pure solvent, and TB would be the boiling point of the solution. Now, because the boiling point of the solution is greater than the boiling point of the pure solvent, that means that delta TB is going to be positive, right? And it turns out that there's a relationship between delta TB and the concentration of the solution. And it is given by this equation right here. Delta TB, the elevation in boiling point, is equal to KB, which is called the boiling point constant. I'm going to say more about that, times M. M, remember, is the molality, right? M is the moles of solute divided by the kilograms of solvent, right? So that's the equation which relates delta TB to the molality, and the constant of proportionality will be given by KB, all right? So M is the molality of the solution, and KB is known as the molar boiling point elevation constant, and the units for that is degrees Celsius divided by M. And this is a value that is related to the solvent, not the solute. It's related to the solvent. In your textbook, they have another fancy term for KB. It's called the ebullioscopic constant, all right? So that's the relationship between the boiling point elevation and the molality and the elevation and KB, I'm sorry, and KB. Okay, so that's basically dealing with the boiling point elevation. And this basically, this relationship here and what we have just discussed here is exploited in several applications. For example, the coolant that you pour into your radiator, or well, that circulates through the radiator in your car engines, right? It's actually an aqueous solution of a compound known as ethylene glycol, right? Which is antifreeze. And what the ethylene glycol does is that it elevates the boiling point such that under hot conditions, the engine won't overheat too much because the boiling point of that solution is higher than the boiling point of water, all right? So that's basically one application of what we have just covered right here. Okay, any questions about this? Any questions? Any questions? Okay, so let me see here. Maybe I should stop here and go back to the assignment to see what questions we can do. So let me go here. All right. So this is question number 5. Let me just check something here. That's question number 6. Question number 7. Okay, you know what? Let me start with question number 5. Now, question number 5, let me get some water. Question number 5 says, if I add 45 grams of sodium chloride to 500 grams of water, what is the vapor pressure of the solution? And it says that the vapor pressure of pure water at 25 degrees is 3.17 kilopascals. All right, so the equation that you're going to use for this, let me write it up here. is vapor pressure of A is equal to the vapor pressure, is equal to the mole fraction of A times the vapor pressure of pure A. This is Raoult's law, all right? So this is the equation that we'll be using in this question, right? Now, the question says that you're adding 45 grams of sodium chloride to 500 grams of water, right? And what is the vapor pressure of the solution? And it gives you that the vapor pressure of pure water is 3.17 kilopascals. So the first thing I'm going to write down here is that the vapor pressure of pure water is equal to 3.17 kilopascals, all right? And the question is asking for the vapor pressure of the solution. Now, the vapor pressure of the solution, let me help you out here, will be equal to the vapor pressure of pure water plus the vapor pressure of sodium chloride, right? But remember now, sodium chloride is a solid. So that means that the vapor pressure of sodium chloride will be equal to 0. So therefore, we can simply put that the vapor pressure of the solution is equal to the vapor pressure of pure water, all right? Or not pure water, I'm sorry, water itself in the solution, because we have the vapor pressure of pure water here. Okay, so my question to you is, how do we get the vapor pressure of water? And the hint lies in Raoult's law. Okay, so I'm open for any ideas, suggestions, whatever. Any ideas? Okay, so yes, you're right, Alexandra. We need to calculate the mole fraction of water. Okay, so mole fraction of water. How do we calculate that? What's the formula for calculating mole fraction? Let's deal with that. Okay, so this is H2O. Okay, let's see what's in the chat. Well, somebody's saying mole of solute per liter of solution. Nope, that's not it. That is molarity. You're confusing molarity with mole fraction. Okay, somebody said mole of solution. What do you mean by that, Miss McConnell? I think you need to say more.
It's the mole of the solute divided by the mole of the solution.
Okay, so you're saying moles of, you sure that's right? We're talking about the mole fraction of water, right? So moles of what? What goes up top as a numerator in this equation?
Solute.
Hmm?
Solute.
I didn't get that. You sound kind of muffled. What would be up here as a numerator? Moles of what?
Solvent, water.
H2O divided by what?
Total moles.
Total moles. Okay, very good. So we need to find the moles of water, and we need to find the moles of the other substance, and then we add them together, right? And the other substance is what? What's the other component of the solution?
NaCl.
NaCl, right. Okay. So let's find the moles of NaCl firstly. Moles of NaCl, how do we calculate that?
You convert the given gram amount using molar mass to get moles.
Okay, so 45 grams, and then we multiply that by 1 mole over the molar mass, which is 58.44 grams. So let me write that down here. 58.44 grams. And according to my calculation, this works out to be equal to 0.77 moles, all right? And then we do the same thing with water. Moles of H2O would be equal to the gram, which is 500 grams, multiplied by 1 mole over 18.02 grams. And that is equal to, according to my calculations, 27.7 moles, right? So the total moles would be the sum of those two, which is equal to 28.5 moles. So I'm going to put 28.5 moles here. Okay, so that means that to calculate the mole fraction, we need the moles of water and the total moles of everything in the mixture. So the moles of water we calculated to be equal to 27.7. And the moles of everything would be 28.5 moles. And that would be equal to, oh, I didn't work that out. Okay, let me work it out here. 27.7 divided by 28.5. So according to my calculation, this works out to be equal to 0.792. 0.79, I'm sorry, 972. 0.9, let me erase this here. .972, all right? So that's the moles of water. But we're not finished yet because what the question is asking for is the vapor pressure of the solution, right? So how do we get that? And the hint is right here again. The hint is right here. So now that we get the mole fraction of water, so how do we get the vapor pressure of the water in the solution? What's the formula to calculate the vapor pressure of H2O based on this equation? Imagine using H2O instead of A, right? The vapor pressure of H2O would be equal to what? Oh, I haven't been checking the chat, sorry. Okay, so Megan, you're saying multiply by 3.17. Okay, that's correct. That's actually the point I was trying to get at in asking the question. But let me just do it like this. Mole fraction of water multiplied by the vapor pressure of pure water. So we know what the mole fraction is, which is 0.972, multiplied by the vapor pressure of pure water, H2O, which is the 3.17. So we're going to put that here. I'm sorry for the mess, folks. Don't have enough space to write down here. So it's going to be 0.972 times 3.17 kilopascals. And let's see what that gives. So that's 0.972 times 3.17. So according to my calculation, this works out to be equal to 3.08 kilopascals. And that would be the final answer to this question. Okay, any questions about this example? Any questions? Okay, may I clear all this? Oh, hold on. Oh, okay, so Alexandra is asking about the 25°C information given, if that's a factor, and the answer is no. That is just thrown into, I guess, confusion. But no, because we're assuming it's the same temperature that, you know, everything that we're doing applies to. So the 25 degrees Celsius does not come into play. Okay, any other questions? Any other questions about this? Any other questions? Okay, do I have your permission to clear all of this? All right, so let me, excuse me, all right, and let me scroll down. Okay, so let's look at this question here. Now, this one is one of the usage of, let me see here. Yeah, this is one of the usage of colligative properties. We can use it to actually calculate the molar mass of a solute that is dissolved in a particular solvent by looking at the changes in the vapor pressure of the solution compared to the solvent. Okay, so this question says that you have a solution that is prepared from 96.0 grams of the solute in 5.25 moles of toluene, and the vapor pressure of that solution is 0.161 atmospheres at 60 degrees Celsius. So the question is asking, what is the molecular weight of the solute? And it gives you some additional information that the vapor pressure of the pure toluene is 60 degrees Celsius, or at 60 degrees Celsius is 0.184 atmospheres. All right. So the first thing I would do to solve this problem is okay, so the first thing I would do is try to find the mole fraction of the solvent in the solution. So the vapor pressure of, hold on, what am I looking at? Okay, so the total pressure, let's start off with that. The total pressure will be equal to the pressure of the solute plus the pressure of the vapor pressure of the solvent. Now, because the solute is a solid, that means that the vapor pressure of the solute is equal to 0, right? So that means this reduces to the vapor pressure of the solvent, right? Which is toluene. All right, so let me do this. Let me change this here. Instead of having solvent, since we know what a solvent is, I'm just going to change that to toluene here. I'm just going to put TOL for toluene, all right? So basically, all we need to do is find the vapor pressure of toluene, and the expression for that would be the vapor pressure of pure toluene times the mole fraction of toluene, all right? So basically, we can find the mole fraction of toluene as being equal to P toluene divided by the vapor pressure of pure toluene, all right? So we know what the vapor pressure of pure toluene is, 0.184, and the vapor pressure of the resulting solution is 0.161. So I'm going to put 0.161 atmospheres above, and down here I'm going to put 0.184 atmospheres. And when I calculated those two, I got 0.875 as the mole fraction of toluene in the mixture. Now, the mole fraction can also be, by definition, be said to be equal to, let me do this over here, the mole fraction of toluene. That will be equal to the number of moles of toluene divided by the total number of moles. So this will be N total, TOT, right? Okay, now, as far as the number of moles of, the total number of moles, we can write that to be equal to the number of moles of toluene plus the number of moles of the solvent, and that up here would be the number of moles of toluene, right? Now, here's where things get a bit tricky, because what we need to do is find out the total the number of moles of toluene based on this setup. And the number of moles of solute, I should say, solvent, I should say, based on this setup. So how do we do that? Well, we have some numbers to play with because let me see here. We're given a number of moles of toluene, 5.25, right? So basically this would be equal to 5.25 moles divided by 5.25 moles plus the number of moles of the solvent. And that will be equal to the 0.875 that we worked out right here, right? So this goes here, all right? And basically what we need to do is solve for this. Now, I'm not going to go through all the steps. I leave that for you to figure out, but it's basically algebra. If you go through the steps, what you'll find is that the number of moles of the solute, hold on 1 minute. Yeah, this should be the solute. I'm sorry, not solvent. Right? So the number of moles of the solute, when you work this out, it turns out to be equal to 0.750 moles. All right? So therefore, the molar mass will be equal to the mass in grams of the solute divided by the number of moles of the solute. Now the mass in grams they gave us for the solute is 96.0 grams divided by the moles, which we calculated to be 0.750. And we worked that out, and according to my calculation, this works out to be equal to 128 grams per mole. 128 grams per mole. So this would be the final answer right here. All right. Okay. Any questions about this example? Any questions? Any questions? All right. If there are any questions, you can hold off on it because I'm going to take another break. Or actually, you know what? Let's continue because the class ends at 1:10 anyway. All right. So just to be sure, any questions about this one? Any questions? Any questions? Okay. Can I clear all of this? Can I clear this, folks? Going once. Going twice. Okay, let me clear it. And we're going to move on to the next question. I don't know if we'll be able to finish it in time. Okay, but we'll try. So let me scroll down. Okay. Oh, no, you won't be able to do that one yet. Actually, yes, you should be able to do this one. All right. Now, the key to solving this one is this equation. Let me squeeze it up here. It's delta TB is equal to KB times M, right? Remember, this is the elevation and boiling point. This is the molality. And KB is the boiling point constant. All right. Okay, so the question is asking, what is the boiling point of a 2.4 M, and this is molality, 2.4 M solution of glucose, and it gives you the boiling point of pure water being 100 degrees Celsius. So how would you tackle this problem? This is a relatively simple problem. Anybody with any ideas?
Would you take 100 times 2.4?
No. Because you need the KB value. So maybe I didn't tell you this, but the KB value is a constant. And that would have to be provided by yours truly. So let me do that now. Let me just show you this table right here. This table gives the KB value for different substances. And I'm talking this column right here, right? For water, the KB value is 0.52, all right? And this will be the units, degrees Celsius over M. So let me go back to the question itself. So basically, KB will be equal to 0.52. Let me write that down here. KB will be equal to 0.52 degrees Celsius over M, all right? So to answer your question, who asked that question? I didn't see who, was it Miss McConnell?
McCoy.
McCoy, okay. Delta TB would be equal to KB, which is 0.52 degrees Celsius over M, multiplied by the molality, which is 2.4 M, all right? So 0.52 divided by, not divided, multiplied. 0.52 multiplied by 2.4. So according to my calculations, this works out to be equal to 1. Okay, I have to round this off to 2 sig figs. So this will be equal to 1.2 degrees Celsius, right? So remember now, that represents the elevation, which means that the boiling point, TB, will be equal to the boiling point of pure water plus the elevation, which would be 100.00 degrees Celsius plus 1.2 degrees Celsius, and that would be equal to 101.2 degrees Celsius. So the boiling point of the resulting solution is going to be 101.2 degrees Celsius. And that's how that is done. All right. Okay, any questions about this example? Any questions? Any questions? Okay, not much time left anyway, so let me just say that, so just to remind you of what will be happening from now on. From now on, you'll be watching the videos. Now, I did not get to complete all of this chapter, so I have made available in Canvas. Let me go to Canvas. Let me go back to sharing my screen. And then let me go to files. Okay, so just to remind you, the videos that you should be watching between now and next class will be under the module section. So when you click modules, and then you're going to go to where it says colligative properties of solutions. So basically what we have done so far is up to boiling point elevation. We have not done freezing point depression. So I'm going to leave this, all of this for you to watch all those videos. I've already covered the first 1, 2, 3, 4, 5. I'm part of 6 videos. And then, so, you may want to watch those over just to, make sure that everything is fresh in your mind concerning those topics that we just covered. And make sure also that you watch the other videos as well. And we'll come next class and discuss the rest of the problems in assignment number 1, all right? Let me see, somebody has a question. Where do we upload the syllabus acknowledgement? There is a Dropbox available for you to do that. You go to assignments, and you should be able to identify the Dropbox, and then you can upload your syllabus acknowledgement there. All right. Okay. Any other questions before we leave? We have 1 more minute. Any other questions? No questions?
I have a question.
Oh, yes, ma'am. Sorry.
Do you upload the PowerPoints that you use?
They should be available. Let me check and make sure. Yeah, I normally make them available. Let me check and see. Okay, lecture notes. So go to files, and then lecture notes, and that's where you'll see the PowerPoints. So this one is made available for you guys, which is what I was teaching from today. All right. Okay, folks. So I'll see you guys next Monday. All right. Take care, folks.
I have a personal question about the testing centers.
Okay. I mean, if you're okay with other people listening.
Yeah, I mean, it didn't apply to everyone else. I don't want to.
Okay, yeah.
Yeah, no. So I'm in Massachusetts.
Okay.
So is there testing centers up here or some sort of?
Yeah, there should be. In fact, tell you what, let me write down your name.
Okay.
So that I can talk to the testing center people here, because there's like a network throughout the country. You know what I'm saying? So
Yeah.
even, you know, some college where you are located. What city in Mass are you in?
Hanscom Air Force Base.
Oh, okay. How do you spell that?
HANSCOM.
HANSCON. Air Force Base. Okay.
Yes.
I will inquire about where you'd go to do that.
Okay. Thank you.
Testing center. There was somebody else. Who was it? Was it you, Mr. Lozano?
Yeah.
Yeah. So okay, let me get your name down before I forget.
It's-
Lozano.
Yeah.
But you're
it's-
in Orlando, right?
Yeah, I go to UCF. I'm just taking this class as a transient student.
Oh, so that means okay. So UCF, that should be the testing center. There should be a testing center there.
Yeah.
All right. So let me make sure I have your names down. And for the rest of you, if you're in a similar situation, let me know. All right.
I am also in a similar one.
Oh, okay. Hold on. So this is Megan.
Because right now
Mhm.
I'm in Gainesville because I go to UF. So I'll
Okay.
be at a testing center there. But then at the end of July, like
Mhm.
towards finals week, I'm going to be in Texas.
Oh, okay. So let me write down first Gainesville and UF.
Yeah.
So as far as the Texas move is concerned, do you know what city?
Mansfield, like Grand Prairie, Mansfield area.
Mansfield. All right. So I will definitely inquire about that as well.
I have a quick question.
Yes, sir.
I haven't been to the campus in Ocala. Where's the lab at today?
Oh, it's in building 2, room 125.
Okay.
Mhm.
Thank you.
All right, no problem. Okay, there's a question in, oh, you just asked that question. Okay. All right. Any other questions before I go? Any other questions? All right. Take care, folks. See you Monday.